All right. Okay, it's a great pleasure to tell you a little bit about keeping track of phases. This will be, I guess, a little bit improvised. And the goal is to understand something about the groups of Gaussian states and Gaussian unitary transformations, and the relationship between the classical groups as they act on the phase space and their representation as unitary operators acting on Hilbert space. So complex phases for Gaussian unitary transformations. And I think I will try to really just work through a single example and illustrate most of the things that are relevant for this single simple example. So we consider one bosonic degree of freedom. Okay, therefore, classically, we have coordinates Q and P as coordinates in phase space. So formally, Q and P are linear observables, so they are elements of the dual phase space. But in the quantum theory, we have operators Q and P as quantum linear observables. Then we have our equivalent description. We can have an annihilation operator and the creation operators that are the standard linear combinations of Q and P. And we can look at the space of quadratic operators. Consider space of quadratic Hermitian operators. Which I can write as, I call them H, but we can discuss in a moment how physical they are. So quadratic means I can have something like, let's have a real number A times Q squared plus B times P squared. And then we can, of course, also have something else, Hermitian, which we can write as QP plus PQ. Now that's the third operator that's also Hermitian and quadratic. So from that, we see that the space of these quadratic, of course, I could then always put plus D times the identity as quantum operator, but that's not so super interesting. That's just adding an additional identity. So we see that the space of quadratic operators that are Hermitian is three-dimensional. And in fact, we can describe this space as as a Lie algebra. We can ask if we have the commutator of two such quadratic operators. So let's call the commutator H1 being of this form and H2 of this form. It will be again quadratic. Yeah, so here we would have A1, B1, C1. Here we would have A2, B2, C2 as variables, and then whatever comes out there, it will be, I don't know, we can call it H3, where our coefficients A3, B3, and C3, they would be as functions of A1, A2, and so on, all the other ones, just the standard commutation relations. And what I'm claiming, and I guess Tommaso has already stated that before, and I discussed that at other points, that we can describe the space of H as Lie algebra SP2R. And well, here I didn't properly write it as a Lie algebra. The proper way would be with a small s. So SP2R. So those are 2 by 2 matrices.
So, I have a basic question about
Yes.
the dimension counting that you did. So how about also like the PQ minus QP with pure imaginary coefficients? Would that be like already within the span of these, or
You mean QP minus PQ?
yeah, with pure imaginary yeah.
Well, we remember by standard commutation relations that QP, that this is just I times H bar, and therefore this whole thing, I times this, will be proportional to the identity.
Got it. Okay, thanks.
No, that's a good point. Yeah, I just didn't discuss that of course using commutation relations, this linear combination doesn't exist, or is not independent. So we find that we get 2 by 2 matrices that are traceless. So that's in fact everything that needs to be said about the algebra of SB2R, because this actually happens to be the same as SL2R, which is a consequence of the low dimensionality. In general, like I can just say, in general, we have 2n by 2n matrices such that I usually call it K. So the matrix I call K, such that K times omega plus omega K transpose is equal to 0, where omega in our standard basis of Q and P, I usually like to write like this, with respect to Q1 up to Qn, P1 up to Pn. And I can tell you even specifically how the relation is. So this is really Hermitian quadratic operators as representation of SP2NR. And the relation goes as follows. I define, okay, there are various ways to do it, but one way is to say H is equal to 1/2 HAB psi A psi B, where psi A is essentially the structure of Q1 up to Qn that I just introduced, but then also P1 up to Pn. So this will be in general the most, I mean, this will be the most general quadratic form where H is symmetric. HAB is equal to HBA. And from that condition, I can immediately count what are and real. What are the number of independent real entries in a symmetric 2n by 2n matrix? Well, it's n times 2n plus 1 independent entries that also agrees with the dimension, namely the dimension of the symplectic algebra 2nr is equal to n times 2n plus 1. Now, if I want to think of H as an operator that acts on, that generates unitaries, I would write U being equal to e to the minus IH. So that means the proper generator, I would call K being equal to minus IH. That's kind of the quantum operator that generates my transformation. And I want to relate to classical Lie algebra element K. And K is supposed to be a linear map on the classical phase space, which is essentially our matrix representation in SP2NR. And we can just calculate it explicitly by using the commutations. So I think I should copy this over. Let me, this is the first time that I'm using this kind of fancy iPad things for such a purpose. So let's see if it works well. So let's introduce here a new sheet. Let's copy that in here. So that's kind of what we should remember. And what I'm now saying, let's do it in red. We remember maybe from Tommaso's talk or more general that we have U psi hat A, U dagger U, that this is equal to some matrix AB acting on psi. Now, if we have this one is a quadratic, is a Gaussian unitary. It's generated by a quadratic operator, so Gaussian unitary. Now, if I have that on two sides, this I guess I can call the adjoint action. Now, whenever you have something like U dagger U, this is the adjoint action because you have kind of the inverse times the other one. Then we find that the adjoint action of the unitary on psi gives us a representation of a group. In this case, MAB will be element of the symplectic group. And now I would like to do that in a generator way. So what's kind of a small perturbation, and for that we just do I mean, in essence, the way you can write it is we say u of epsilon being equal to e to the minus I epsilon h, and then we take the derivative of well, let's maybe even write it like this, u epsilon. Then we can write u epsilon dagger psi a u, and take the derivative in epsilon, evaluated at epsilon equal to 0. And what we should find is that this will give us the commutator of IH with psi a. Which we can now evaluate. So let's plug this expression in here. So we have the commutator of 1/2 HAB psi A psi B. Commutator, well, now that I already used A and B, we should call this psi rather psi C. Yeah, let me move. I mean, this is not part of the equation, of course. Let's move that further away. Exactly. Let's refer this to psi C, and now we can, of course, use the standard moving stuff out. There should be an I in front, and we get I over 2. HAB we can take in front, and then we have parenthesis psi A times commutator psi B with psi C, and plus then we take psi B out, so we get commutator psi A with psi C psi B. And then we remember for the commutators that the commutator of psi A with psi B is equal to I times omega AB. That's just a standard commutation relations using the symplectic form, which in the case of just a single degree of freedom, this would be just 1 minus 1, just the block matrix. So with that, we would get here minus omega, sorry, not minus, plus I omega BC, and here also I omega AC. So we can write, we can now combine that. The I will give us a minus 1/2 in front. And now I can, well, rearrange that a little bit and write it as HBA. Remember that H was symmetric, then psi A. And then I have the omega BC in front. That's the first term. For the second term, I have HAB psi B, and I have an omega AC in front, and there is a plus in between. And of course, I can now relabel my indices and just write this. So first of all, I can interchange B and C but omega is antisymmetric. So recall omega AB is equal to minus omega BA. It's an antisymmetric form, BA. With that, I do the same thing here as well. And I pick up a minus sign that cancels the other sign. And so overall, I will find that this is the same as omega C A H A B psi B, where the 2 here was cancelled from the fact that these 2 terms are actually the same after relabeling of the indices. Now, because the only free index is the index C. That is in both cases the same, and I bring to the front. And so this object I can call KCB, and it satisfies the condition of being an element of the symplectic algebra. Any questions at that point? Or was that all review? Okay, I see.
Good.
So at this stage, I hope we so now, of course, you can rewrite your H in terms of the indices of K. So established relation K such that K omega plus omega K transpose is equal to 0 is equivalent to K hat being equal to, and now one needs to remember that a little bit, that this is 1/2 psi A psi B with the HAB. And if you look at this equation here, we said omega A B HBC is equal to KAC. So we can solve this for HBC being equal to KC A, and then here omega inverse BA. And I often refer to this object as little omega BA. And so with that, plugging this expression in here, we can find that this is 1/2 little omega AC KCB, which overall C is contracted, so it has open indices A and B, and that's contracted with our psi's. So now we have and of course here in abstract indices that would be A B omega BC plus omega A B K transpose BC being equal to 0. So we now have a relation between symplectic matrix K and a quantum operator K. And a calculation confirms, that's kind of like a homework, that if you take the quantum commutator of K K1 times K2, this is the same as if you first took the commutator of the corresponding matrices, the 2n by 2n matrices K1 and K2, and then constructed the operator using this rule. And that kind of establishes that K is indeed a representation of the Lie algebra. No, the K hats have the same commutation relations as the matrices K. And so what one would now think, exponentiation yields a representation of group. No? So we have K element SP2NR algebra. Therefore, e to the k should be a representation of the group SP2NR. But now, k hat is element of representation, rep of SP2NR. Therefore, e to the k hat element a representation of SP2NR, exclamation mark, question mark, is that true? And the answer is no. There are complex phases that are a little subtle and that we will see explicitly by looking at a very, very simple example. Let us look at K being equal to now I need to think. Let's actually start a bit different. Let's start with H being 1/2 number operator plus 1/2. No, the good old harmonic oscillator, which we can also write as 1/2 q squared plus p squared, from which we can read that HAB will be just equal to the identity matrix, no? Because if I contract HAB with psi being q and p, this one will give a rise to q squared, and this one will give rise to p squared. Great. So therefore, K being equal to omega times H, we can construct the Lie algebra element being equal to -1 times 1, 1. So therefore, our K will just be this 2x2 matrix, and our corresponding K hat will be -I times H. So it's just -I times 1/2 number operator plus 1/2, or equal to -I/2 q squared plus p squared. Let's look what happens if we exponentiate e to the k. E to the k is equal to, and for that let me use Mathematica, but I'm sure you will be able to actually see it very quickly, because of course this is just an element in SO2. No, it's the exponential of an antisymmetric matrix. If you take that matrix X, and let's maybe introduce a coefficient epsilon, then you find.
Lucas, are
Yeah.
you showing Mathematica or?
No, I don't.
Okay.
Yeah, I mean,
it's like
it's just a rotation matrix. I just checked it for myself because my memory, I sometimes I make mistakes. So
yeah.
it's really just sine.
Or in quantum info, it's just exponentiating the sigma y, and that's it.
Exactly. Yeah. Maybe I should not have called it epsilon, but
No, fine.
But theta. But in particular, we see that here our representation is epsilon is is 2 pi periodic. Okay, so in particular, e to the 2 pi k is equal to the identity. You agree? But what happens if we do the same thing for our quantum operator? So that's we saw for k being equal to 1 minus 1 that e to the 2 pi k is equal to the identity. And we remember that k hat was equal to minus I over 2. Oh, sorry, actually, I made a mistake here. Of course, here is not a 1/2. Here is not a 1/2. No, the 1/2 only exists in front of the Q and P. So that means we can write this as Q squared plus P squared, or as minus I times n plus 1/2. So now let's have a look. What is e to the 2 pi times k? Well, this will be equal to e to the minus I 2 pi times n plus 1/2. Now, all the eigenvalues, spectrum of n is equal to the natural numbers starting from 0. And of course, we know that I times 2 pi times an integer is, if we take the exponential, is just equal to 1. Therefore, overall, we find that this is the same as e to the minus I 2 pi times 1/2. Because all the integers don't matter. We cancel the 2, and we arrive at this beautiful formula e to the minus I pi, which we know is minus 1. And of course, here as an operator, this is the identity operator. So we see that this is not equal to the identity operator because it's minus the identity operator. From there, we see immediately that e to the k is not a proper representation of SB2NR, or in this case, in this specific case, it's of course SB2R. But what is it instead? What do our unitary Gaussian transformation, what does it represent? And the answer is it represents the so-called double cover, also known as metaplectic group. E to the k hat gives rep of MP2NR, where this is called the metaplectic group. Who of you is familiar with the metaplectic group, apart from Tommaso, who of course knows it? I don't know, Marek, if you have worked with it or?
Yeah, I always hear that term, but if you can So you define the symplectic group. Is there some concise, set that you can say MP is equal to a set of matrices?
No, so there does not exist a finite dimensional representation. That's kind of what you're asking for. There is a way
like
to
this. Okay.
model it, but I will first just draw you what it is. So I will try to illustrate it, and for that, I will explain it metaplectic group MP2R. And for that, let's start with what is the symplectic group. So here, metaplectic group as that.
So, but is it defined as the exponential of those? So is there an abstract definition now of the metaplectic group, or is it defined through this representation that you just described?
Both. So there is a way to define it abstractly. There is also a way to, the bosonic Gaussian transformations actually are the best known representation of this group. So this is a faithful representation, Gaussian unitaries. It's an infinite dimensional representation, but that's not in principle. I mean, that's not a problem. Let's develop an intuition for what it is. And for that, let's draw SP2R. So remember, SP2R is actually the same as SL2R. So 2 by 2 matrices with unit determinant. Now, it's not so easy to know a nice parametrization, but there exist some nice parametrization of the metaplectic group, and I will just give you one. And I would like you to believe me that this is that this essentially covers all 2 by 2 real unit determinant matrices. And because my memory isn't great, I need to look up this example that I kind of give all the time, and it is given. So M is the matrix, and it looks like there we have it, as cosine of phi cosh of R plus cosine of theta times sinh of R. Oh, do I want to use that parametrization? Yeah, it's fine. And then I have sine of phi cosh of R plus sine of theta, and again sinh of R. That was the first two, and then I have here the remaining entries, again sine of
Phi, I'm guessing.
Yeah, so this should be I wrote a terrible example here. Gosh, and yeah. Really, do I don't have a better one? Okay. Okay, let me actually check in another paper. I think I used a different example. I mean, it's the same parameterization, but I think this one is a bit nicer written. It should be correct what I wrote, but I just want to make sure to give a nice example.
So it's like 3 variables. Phi are
exactly. It's 3
theta.
variables, and
so over reals, I will have 4 matrix entries, but it's symmetrical and has unit determinant.
yeah. So okay, I have it now here, and I just switched to a slightly different naming. Yeah, I even keep the theta. So I just call this one tau, and then I have here minus sine tau cosh r plus cosine theta sinh r, and then I have here cosine tau cosh r plus sine theta sinh. And essentially, if you calculate the determinant of M, you find that it's 1, and you can even show those are all the matrices that, I mean, every 2 by 2 matrix with unit determinant can be written in this form. And what we should notice, tau is 2 pi periodic. And theta is 2 pi periodic. But even more, if r is equal to 0, it actually becomes theta independent, not because all of these singes vanish if r is equal to 0. So that means at r equal to 0, it's theta independent. So based on your knowledge of polar coordinates, you can therefore think that r theta are polar coordinates of a plane, polar coordinates. And tau is a circle coordinate. So it's a 2 pi periodic coordinate. So what do we get if we combine a circle with a plane? Let's try to draw it. We have a plane where essentially we have some origin, where the origin corresponds to tau equal to 0, theta equal to 0, and r, or well, theta is actually doesn't matter. We have r equal to 0, and theta is arbitrary. And if you copy this formula and check the entries, you will see that this corresponds to the identity. Let's place that somewhere here to the side. And let's if we call this M of well, we can call it tau r theta. Then we have M of 0, 0 theta will be equal to the identity. So that's the identity, and an arbitrary point in here we can measure with radius r. I mean, this is really just a picture. and the angle theta. That gives us the plane. So that's in principle infinitely extended. But now the statement that tau is 2 pi periodic means we get the product of these planes, which has length 2 pi. So so as a manifold, we have that SP2R is equal to, well, a plane, which is R2, tensor product S1, or of course you could also write it as U1. So in particular, the plane up here is like, you can think of it as a portal in the game. Portal is identified with the plane here underneath, identified. And what is the double cover? The double cover of the symplectic group is really nothing else than gluing 2 copies of the symplectic group together. So the metaplectic group is essentially the same set, but you have another copy here and down here. So
it's 4 pi periodic, or you?
Exactly, it's 4 pi periodic, which we actually saw. No, we see that e to the minus I. Let's introduce here parameter tau number operator plus 1/2 is 4 pi periodic.
Mm. And in this case, this kind of topological gluing, this identification of up and down the portal, there's only one portal again, right?
Exactly. So we will still identify this with the one down here, but essentially the new thing that we have is that we have a point. So we have here the identity sitting, and if we now go, so previously we had minus identity here. Now that's where minus identity in the symplectic group is. In our case, we found, or I mean, this is something that you can check, e to the minus pi n plus 1/2 operator. This is of course not equal to minus the identity in as linear operator in the Hilbert space. So let's draw in black. In black is essentially the symplectic group. Black equal to SP2R. And then let's draw in orange. In orange, of course, we would have here still the identity, but then at these two, at this point here, we would have e to the minus I pi n plus 1/2. Here we would have a different operator, namely e to the I pi n plus 1/2, which is different. And then at the bottom here, if we go even further up, that would be if we move by 2 pi, by plus 2 pi or minus 2 pi. So this would be e to the minus I 2 pi n plus 1/2, which we calculated is minus identity. And that's the same point if we go down here, which is e to the plus I 2 pi n plus 1/2 being also equal to minus the identity. So that means orange is equal to the metaplectic group 2R. And of course, what I haven't told you in detail yet is how you make the group operation work in here. But essentially, every point in here has a corresponding antipoint outside of it. Yeah, so here M element sp2 R, and then we could call this somehow M bar, which is kind of the second copy. Yeah, element sp2 R bar, and we can glue these two copies of sp2R together to form the metaplectic group. So
so you consider the interiors. So consider the interior of this symplectic group, right?
yeah,
And then the boundaries you glue, right?
Yeah, I mean, yeah, exactly. Yeah, you glue them around the boundaries, but of course each boundary will appear exactly once. So that means you still you have exactly 2 times the number of elements as in the symplectic group.
Okay. And Lucas, this parametrization that you constructed, is it meant as a manifold isomorphism, or is it really the equality that you have here? So this symplectic 2R, is it really equal as manifolds, or it's isomorphic?
I don't know what you mean. What the difference between you mean this one? Yeah. So as a manifold, this is a diffeomorphism. Essentially, what I wanted to emphasize is that it's not. Oh no, I guess that is actually your question. So you mean, is it isomorphic as a group? And there the answer is no. So if you think of R2 as the group of vectors and S1 as U1 as the group of multiplication of on a circle, then of course neither sp2R nor mp2 are isomorphic to this as a group. But of course, you see, by just gluing 2 versions onto each other, you don't change the manifold. Like, it's really the multiplication on it that is different for the metaplectic group compared to the symplectic group.
Okay.
And so in general, so maybe to just round up, and I mean, I really won't be able to tell you much more in the summary, but for every M element, the symplectic group 2NR, there exist 2 Gaussian unitaries UM1 and UM2, which of course the 2 they just differ by a sign. So it's just UM1 and minus um1. Yeah, just these two. I mean, you could also just write them as plus minus or something like that. But there are two Gaussian unitaries such that UMI dagger psi A UIM is equal to MAB psi B. Yeah. And now in general, we will have something like UM1 times UM2 is equal to, and now we have the sign ambiguity of U1 times UM. And so this means that it's a projective wrap of SP QNR or proper representation of MP QNR. And so, of course, if you want to do calculations, it will be relevant to figure out these signs, because if you take superpositions of Gaussian states, for example, these superpositions will be relevant. I mean, these signs will be relevant. Yeah, that's essentially what I can tell you at this stage.
Super. So metaplectic group and symplectic group have the same base manifold, just the multiplication is different?
You could say it this way, but this is not in general the relevant property. So for example, if we go to the spin group, I mean, if we go to fermions, we have the same structure. Everything that I said goes through in the same way. That there you could do your Hamiltonian being 1/2 number operator minus 1/2. So sorry again.
Yeah.
Without the 1/2 in front. That would be again a double cover. In this case, you would have SO QNR, which would be your matrices and algebra, and then you would get the double cover, which is the spin group of 2NR, which you might be familiar, of course, if you have SO3R, the double cover is SU2, which is also the spin group, spin 3R. And that generalizes in other cases, but they are, yeah, the manifolds definitely change. They are glued together in a different way because the spin group is actually simply connected, so you can contract circles, while in SO2NR you cannot contract circles. Now, in the case of the metaplectic and symplectic group, you cannot contract circles in either of them if your circles go vertically. Essentially, it comes from the fact that in SB 2N and also the metaplectic group, you always have a UN sitting as a subgroup, and the UN has a circle that's non-contractible. And in the case of the metaplectic and symplectic group, you can never contract this circle from the UN. While in the case of the spin group and the special orthogonal group, in the special orthogonal group, you can still not exactly contract that circle, but in the spin group, you can contract these circles. Yeah. So yeah, I can probably talk about that at another time a little bit more. But the key question that I'm not answering in this talk, Tommaso and I and a collaborator have a paper that I was supposed to finish like last year in April, but then due to kind of personal reasons, lots of things have been delayed. But I hope to get back to that. I mean, like soon. And there we essentially develop a method to understand how to get these signs properly by having a have a way to describe the metaplectic group in a nice way. Oh yeah. I actually didn't realize that
very cool examples.
Yeah, that I didn't have my video on. Sorry about that. Yeah. But yeah, it actually kind of worked with the iPad. And I actually will need to leave, so maybe I should stop the recording. Yeah. Okay, I need to do it here.
So on the iPad, stopping I can cut it later.
Okay.